Yeah, go ahead again.
Okay. So today I'm going to present FTLSim, a high-speed, lightweight flash translation layer simulator. So at first I will go through the building process and the compilation process and the basic structure of the simulator and how to run a successful simulation, and then I will show some results regarding that. So this is flash translation. FTLSim is actually SSD simulation framework, but fully focused on the FTL transaction, how that do the transactions of data requests depending on the block traces. So I will talk about the block traces later, but this is the main important part of this simulator. And these are the download links. The first one is the basic who actually made this whole source code, and the second one they have extended this and made it quite better, added the wire leveling model also in this one. So I saw this one is more compact, the second one. And in the directory we will see some of the files. One important thing is like, so the the basic version of the simulator is Python 2.0 based. So typically we don't use now Python 2.0. So the current build system is fully on Python 3, what we use. So the second version they have extended that to Python 3 version, so there is nothing outdated function actually. So in the directory there could be a lot of files. So the only file we need is this one, the FTL, and when we will extract that, we'll get all the simulation files. The others are for actually some dummy traces, and some MATLAB code is also there for the analytical equations. So regarding when we will download that zip file of the simulator, there could be a couple of type of files depending on the uses, and we should know what type of use of which file, so that we can know where we have to change when we are simulating. So typically this FTLSim consists of like some C simulator codes and some user Python scripts and some interface code. So there is like the whole mechanism of an SSD written in C. These are the files, and there is some interface files. These files actually helps to interact between the Python and the C. So these are important regarding when you are using, like, you want to edit the Python file, you have to also edit this interface file uh, depending on your usage. Typically we don't have to change the FTLSim files, C files. Sometimes we need to, if we want to change some garbage collection or wire leveling algorithm, we have to implement some new algorithm. In that cases only we have to change those things. And finally the user Python files. So they have given a bunch of files to play around, and one of the important file is the setup.py that helps us to set up this whole system in our computer or Linux computer. So these are the three categories of files we need to use. So typically a user should use only the Python files. So nothing we have to think about interface or .c until we are changing any algorithms. So the basic flow is this. So there is some simulator files .c or .h. All the algorithms are written there. And then there are some swig interface files. So this is a specific type of Python package called simplified wrapper and interface generator package. So we have to install this before using this simulator at first. And this actually interacts with the Python user files, but through that we are writing our use cases, like how many read, write, and then what should be our user space, what trace we should use. Those things are actually, and also the SSD configuration, everything is written in the Python files. So for that we need a Linux bash command to install the swig. So these are the two commands we have to use.
So this has to be run on Linux.
Yes, it's not Windows. Yeah. So Now, so now we know what files we have. So the second thing is like, as this is in C, at first we have to compile this. All the C file we have to compile at first. This is the first step. So this is the building of the C simulator in our Linux setup. So for that we need this bunch of commands. We have to run this, and then if everything goes on, then we'll see FTLSim build successfully. And we will see these files created after the building process. So once we get everything done, our simulator is ready in our Linux computer. That means those C files are built, and the interface file also. Now this is the flow how we can write a basic Python code to run a simulation. So the first thing we have to do is like traffic generation. So traffic generations means like the request generation from the host to the SSD. So we can actually generate this traffic in three different ways. One is uniform. That means I want to, let's say, 1,000 requests, sequential request or random request. So for that we can use this getAddress.uniform and how many requests I want to make. This is basic plain vanilla. The second thing is if I want to do some like mixed hot and cold user space, in that case we have to use getAddress.mixed. In that there is a lot of actually arguments, that's why I skip those, but we can actually provide how many address space we want to use for the hot and how many for the cold. And the third one is the trace based. So in this case we can download a standard block trace. So there is a specific type of trace what we can download and give our path in this function, and that will automatically translate this to this simulator.
This is how you wrote your ICCT paper.
Yes.
Like you have
Yes.
used trace.
Yes.
Trace based.
Yes, trace based. So we'll talk about the trace a little bit more in detail after this slide. So after that, what we have to do, we have to run our simulator, FTL simulator. So that will run all the page mapped FTL regarding the from the trace, and then physical flash block that will allocate, and then it will run the LRU or greedy, that type of GC policies. Then the third part, this is the most important part of this is FTLSim, because they give us a lot of function for the statistics. So they give us how many external write is happening, how many internal is happening, how many what is the write amplification factor, erase count, garbage collection trigger, a lot of stat they give actually. So they directly created the interface. So that's the best part of this simulator. Rather than we have to write a code and extract those values, it directly gives those stats in one simulation.
In form of plots or
In form of text. Okay, so for running a simulator, uh, uh, there I showed a couple of ways. So to do a trace based simulation, we have to at first know which trace based workload actually we can use. So this is the I guess the best trace repository. It is called Storage Networking Industry Association. They actually open source a lot of traces for to simulate different real workloads. So in this, we have to go to the block IO traces, because FTLSim is even if the MQSim and others also, they are compatible with only this type of block traces. So inside this, we will see a lot of text like this, but simulator actually handles these things. But the problem is these workloads are very heavy. So one thing we can do is like we can convert these workloads to some lighter version that will reduce the time of the FTLSim simulator. That means the simulation time, let's say 12 hours to 1 hour, it can reduce. The way is like, we'll see like there is a lot of things like the latency time, how much request, but in FTLSim that doesn't deal with the bandwidth or those things or the latency. It only deals with the request and the block address. So we can use a converter to convert this and make the whole trace lightweight, little bit lightweight. So what I did actually. I removed all the unnecessary information. Otherwise, it was taking like one simulation took 36 hours almost. So it was like very heavy, and then SSD got filled up with these simulation files. So I wrote a conversion file and then I converted it and then ran the simulation using this command I already showed. So we have to at first we have to import a get address, get ADTR. This is a Python module already made in the simulator, and then we have to just make a class and make an object of that get address.trace, give the file name. So this file should be in the same directory of the where the file is actually, and then we can just run it. So the count means is like how many times I want to repeat this simulation so that I can get some average. Okay, so now we are ready to run a full-fledged simulation. The first thing is like we have to get the trace and define the logical space or the SSD setup. So we can define with this small snippet, and then we have to tell that what is the size of the physical block and what is the over provisioning factor, so that we that can allocate the logical and physical spaces, and define the block size. So here one thing is like they defined block as segment. So we have to think that okay, whenever there is segment, that means that is block. And then we have to create a pool. So pool means that is a specific address space where, or not address space, that will be a specific list where whenever, let's say, uh, a greedy or LRU based garbage collection process is happening. So what will happen there, whenever a block is targeted, that okay, when the GC will trigger, this one will be targeted. So with those blocks, actually a pool is created. So we have to create a pool for that, depending on the threshold we can use.
So an SSD can have multiple chips, multiple
Yes.
NAND chips.
Yes.
Does it assume only one chip based SSD?
Yes. This assumes only one chip is
Only one raw NAND chip.
One raw NAND chip.
But if you have multiple raw NAND chip, can you update this too?
Yeah, I can. I know where to change.
Okay.
Yeah, but the basic version is on this actually.
Only one chip.
Only one chip.
Because those things are important because you have
Die level parallelism.
that
And then
will improve
plane
the
level.
bandwidth.
Yeah, plane level is also there.
Okay.
Okay. So finally, if you have the Python code now, you'll just run this command. It will show all the results in the in your command prompt. So let's start with a use case. So I want to talk about a little bit about the over provisioning factor that is used in the commodity SSDs. So in the standard SSDs, they reserve the vendor actually reserves some fixed portion of the NAND flash as a hidden user space or a spare space that is called over provisioning. So let's say you have your total SSD NAND capacity, but they have the controller or the SSD controller can use 7% of this only, and the user can only use the 93%. The other, so user will see only those part. So whenever you install an SSD, if you just see the properties, you will see there is not actually a 1 terabyte what you have bought. That might be a little bit less. So what most of the part actually invested there. So the over provisioning ratio is the key factor here. So, and depending on the application, the SSD controller companies actually defines this this alpha. So for the same physical capacity, the over provisioning factors can be different depending on the read intensive and write intensive application. So Kingston and Seagate, they develops a lot of SSD controllers, and they define these actually what should be the alpha depending on the. So there is some data center based SSDs, some enterprise based SSDs. So in enterprise, they think about mostly on read intensive. In the data centers, in some use cases, they think about the write intensive, and they higher this over provisioning to lower down the write amplification factor, and we will see how that lowers down the write amplification factor in the next slide. So for this, I have followed a paper analytical model of SSD write performance, where they have actually analytically modeled, and also they developed this simulator. And yeah, so for that they have modeled that, and this is the equation how they modeled the over provisioning factor, how they are connected with the write amplification factor. So write amplification factor is actually the ratio between the internal flash write and the host write. So typically the internal flash write is more than the host write request, because inside the flash there is a lot of things going on, like the garbage collection and the wire leveling. So because of those, the write amplification goes high. So the ideal write amplification factor is 1, but because of the internal flash writes, it goes more than 1. So as we see in the plot, as we increment the over provisioning ratio alpha, the write amplification is going down, and in the table we can see that the analytical write amplification factor and the simulated write amplification factor using the FTLSim is quite a bit similar. And so this is one of the example I started before doing the in-place update simulation, because I wanted to see actually my SSD is working correctly or not. So more spare space means fewer internal writes are required. That means lower write amplification factors. And here is the reference. We can download this all the things to do this simulation. Yeah, so that's all for today.
Good, yeah.